Okay, so this is working now. Can I have the presentation? Or am I supposed to be presenting with my laptop? Yes, I did. Okay. So let me move this. Sorry, I'm tall. Hi everyone. Okay, you guys are tired and it's almost lunch. So, my name is Bonaventure, as Evelyn introduced me, and today I'm going to share a bit of insight about my work combining uncertainty quantification, active learning with ASR models, how they can be adapted to the African context. So, this work I have done it many other friends, and the main question is, yes, we have large language models which are pre-trained on like massively huge data set like on English and Western languages, but what if we actually want to start the training from scratch? Because many works also have shown that it is important to have the pre-trained language in the pre-training set so that it enhances the performance. So what if we want to start from scratch, and if we have small data, how do we actually make the maximum efficiency from the data, and we at the same time ensure like robustness? So this is what this work is about, technically using active learning. And here, okay. And here, this is just a brief overview of active learning, which can be viewed as a kind of semi-supervised learning algorithms in which we are training an agent by model to learn to select in a big pool of different diverse candidates the sample that will be useful for its maximum performance. And there have not been a lot of studies on that, unfortunately. I mean, they've been on machine learning community, but not on the NLP community. But the very few ones have shown that, hey, we can achieve as much as 90 to 99% accuracy with only 20% labeled data. And we know that the flow of any or many downstream tasks that we currently do in NLP are based on labeled data sets. So, in a nutshell, that's technically what unactive learning looks like, where we have the model that we train to be optimized. Then we have the query. That's where acquisition function comes in and related a little bit with Bayesian optimization. Then we have sometimes human experts who annotate the example, but they can also be replaced by a proxy model, which is a type of a real-world model trying to imitate the behaviors of those. And then all of that is appended to the initial data set, and then like we restart. So this is actually very useful and like very data efficient, because it helps us to not have to depend on a very huge and massive data set. And it is also very crucial and very relevant in the context of African languages, where we have very, not only computational, but also resource constraint. So this is, in a nutshell, this is like what the framework looks like. So we have the first part, which is made of like a training data set that we split into two parts, where the second part is mainly like what we call the pool size. This is the sample to which the model doesn't have access during the training, and among which, and that's the set that we are going to query after we train the model in this framework. The second approach is then like to fine-tune, because the goal is to adapt existing pre-trained models to African languages or African accent, whatever the topic is. So we have, obviously not to start from scratch, we use a pre-trained model that we fine-tune. And then using that pre-trained model, we then perform some uncertainty sampling. It can be done with like MC, dropout, or any Bayesian approach. And here, there are also many others, like for instance, like dropout ensembles, all those type of things. And here, what we do is, instead of we actually leveraged two different cases, but the one that worked the best way was when we selected the top K most uncertain sample, which is the samples about which the model has the least, which is also one of the state-of-the-art ASR models at the moment. We tried Hubert, and then we tried also some commercial versions, commercial like ASR models, which in which Nemo falls in. So what we can see is that in a general domain is like technically us speaking here, things like that. In a general domain, what mainly happens is that our approach using that active learning and like adaptation around incorporating the epistemic uncertainty from the model helps achieve better results. Now, we compared our approach also to random, like, okay, what if I don't want to smartly select in my pool of like unlabeled samples, but actually want to randomly just pick them. So the random approach also does not, quite well, but still does not perform as good as the when we select the most uncertain sample. And even when we go on the clinical domain, which is even more complicated with abbreviations and like medical terminologies, we find out that yes, that is where we have the biggest gap between even both of our approaches and the other baseline. And then the both is technically when we combine both of the domains, clinical and general. And you can also see that our method has upper hand, better performance. Now, because we didn't want to rely on the fact that, okay, we just tried to leverage models, we then switched to data sets. So we tried 3 other data sets, Sauti DB, which has been developed by Teju, medical speech, common voices, and here what we can see, like has been like circling the red, is the performance of our approach, the Wave2Vec model fine-tuned in our framework. And we can see that there is a huge gap between all the baseline and all the baseline approaches and our methodology. And it is also important to see that this result has been achieved by using 40% less of the initial data set, whereas everything else has been achieved using the 100% of the data set. So by using around 60% of the entire data set, we were able to outperform by far the performance of those models when they were trained using the entire data set. So this allows us to say that our approach knowledgeable about those language by the end of the entire training. So when we look at the figures from top down, we can see that our approach allows the model to become better and more robust, because throughout the different rounds, we can see, for instance, that the distribution of like uncertainty weather rate across our approach, which is the most one, becomes decreased quickly, rather than the random, which stay more or less stagnant and very high, around 2 or 4 of the metric that we define uncertainty rate. So when we move across the general domain, we observe the same trends. And then when we combine both all together, what we see is also the same trend. So this figure tells us that, hey, this approach allows not only to be able to focus on a diverse set of accents or language, but it also allows the model to become more robust, more knowledgeable about them, and to be able to become better as active learning rounds, adaptation rounds evolves. So in general, I think this study have shown, and many others have shown, that our multi-round adaptive learning approach with uncertain sampling is very data efficient and high performing, and then obviously outperform state-of-the-art models like Hubert, like Nemo Wave2Vec, and it also outperformed with with LM, which is another ASR model which is closer to Hubert. And then we have more generalization because the results have suggested and shown that our approach is model, domain, and data set agnostic. And this ultimately shows that we don't necessarily need to be running after data. We can develop models that are lighter, models that are data-centric, that are very efficient by learning to optimally extract or use all the available information in the set. As small as it could be, we could still be able to outperform and then do extremely well. So I think that was it. And yeah, I don't know if there are some places for questions, or maybe we'll move to the next speaker.